So thank you for the introduction. My name is Martin Strauss, and this work was done in collaboration with Jouni Paulus, Matteo Torcoli, and Professor Bernd Edler at the International Audio Laboratories in Erlangen. One of the most common complaints about the audio mixture in broadcast audio, like TV shows or in movie productions, is the low intelligibility of the spoken dialogues due to loud background music or disturbing special effects. And since the right balance of the dialogues and the backgrounds are influenced by a lot of personal factors, one ideal solution would be to adjust the volume individually for every person according to personal preferences. And in object-based audio like MPEG-H, this is generally enabled, where the individual components are transported as distinct objects and only mixed together at the receiver end. However, there exists a significant amount of archived content without the individual tracks being available. And this is where dialogue separation comes into account. So this can be roughly defined as separating speech from non-speech content in broadcast audio. And the main challenges that come with this is that usually broadcast audio is in multi-channel, so at least stereo. And we work here with really high perceptual quality and using high sampling rates, so most commonly 48 kilohertz. And another point is that, like, generally free, open source, clean reference data is not available to researchers in general. Also, due to these reasons, approaches that specifically aim at these applications are still quite rare, in fact. So if you introduce this problem a little bit more formally, we have here with Y our broadcast audio mixture, which is composed of a simple summation of the dialogue X and the background B, all components of length N and in stereo. So what we aim here is now to estimate the underlying unknown components X and B as an estimation as X hat and B hat, and we want to mix them back together with an attenuation factor and an adapted level of the dialogue to increase the intelligibility without decreasing the actual perceptual quality. And naturally speaking, we would assume we could just use speech separation methods, and they have made significant progress in recent years in single and in multi-channel. However, the proposed systems are largely impractical for the broadcast environment since they introduce a lot of artifacts and also the aforementioned challenges. At the same time, recent advances in music source separation share the number of channels and the high sampling rates that were developed specifically with that purpose. So assuming that vocals in music and speech in dialogues are related closely enough, the aim of this paper was to investigate transfer learning possibilities from music source separation towards dialogue separation with task-specific broadcast data. For our study then, we selected three state-of-the-art music separation models, like the Open-Unmix model, which was the reference system for the CSEC 2018 evaluation campaign. It is a deep neural network based on a bidirectional LSTM at its core, working in STFT domain. The second network is the DSA Spleeter, which is also working in STFT domain, but is more fully convolutional and a unit-like approach. The third one, the famous Conv-TasNet, which is working in time domain. But there's a music separation version of Conv-TasNet, basically. We compared these methods to two systems that were specifically developed for the task. So the AudioLabs Instant Dialogue Cleaner, which is a real-time VST plugin for post-production purposes, and a system we call DNNs, which is the signal separation core of an in-house system under development, also working fully convolutional and in STFT domain. For the study then, we used real-world broadcast material, which was available in various languages and genres, while the vast majority of the content was in German. The genres differed from documentaries to sports to drama, for instance. The data then was hand-cleaned to obtain clean reference signals and downsampled from these initial 48 kilohertz to 44 kilohertz to match the network requirements. We started with the networks from the pre-trained weights for the networks that were supposed to separate vocals in music, and selected a maximum number of epochs to be 100, as well as introducing a learning rate decay and early stopping to ensure or to avoid overfitting of the networks. As a further step, we switched off all data augmentation methods since they varied quite a lot between the methods, and we wanted to minimize the effect of those. The evaluation was done then before and after fine-tuning with the broadcast content, and for this we selected a couple of computational evaluation metrics like the scale invariant signal to distortion, improvement in scale invariant and scale invariant signal to distortion and signal to inference ratio to evaluate the separation performance. And the third metric was a more recent one, the 2F model, which is a scale between 0 and 100 to approximate the outcome of a Mushra listening test. As further orientation, we also retrained the music separation networks completely from random initialization using the broadcast material, and also computed the IRM as a further orientation point. Next to computational evaluation, we also performed subjective perceptual evaluation, doing a listening test following the Mushra methodology. And for this, we intended to create an application-like scenario where the individual components are mixed back together with an attenuated background. Here, to create a reference condition, first the reference background was attenuated by 12 dB compared to the input signal, and we calculate integrated loudness to have a reference component. For the test conditions, the backgrounds were obtained by subtracting the estimated dialog component from the input mixture, and in a further step, to obtain the attenuation factor, we iteratively adjusted the attenuation to obtain the same integrated loudness than in the reference component. And at the end, all the components were loudness normalized. All the items were loudness normalized. Overall, we had 8 test items, which were balanced always 50-50 according to gender, language, for German and English samples, and also to background. So 4 items had a musical background, and 4 more like a noisy background, like stadium noise or environmental noise, for instance. Including the low anchor and the reference signal, the test had 10 conditions using the music separation networks and the 2 developed for these tasks. The listening tests had to be conducted at home office due to the COVID-19 pandemic, with each participant using their own notebook and their own headphones. The participants were fellow grad students and colleagues with various levels of experience in subjective evaluation. So after post-screening the results, 8 listeners accounted for the final outcome. Now if we take a look at the results. So here what is indicated with a base model is the ones that was only pre-trained on music data, and the one with transfer is the one that was fine-tuned on broadcast material. What you can see here is that all 3 transfer learning networks outperform their corresponding base models, suggesting that transfer learning from music separation towards dialog separation is possible. Conv-TasNet here shows the best results, with Spleeter being second and Open-Unmix on the 3rd place. Especially for Open-Unmix, we assume that this might also be due to the fact that it was pre-trained also on much less initial training data for music source separation. these results are further emphasized if we take a look at the ones that were retrained with random initialization. So in the middle here, we see Conv-TasNet retrained completely from scratch. And maybe not so surprisingly, we see if it was initially targeted at dialog separation, we can outperform the performance of the ones based on music. However, looking at the results of the transfer learning version, we see also that the transfer version outperforms the ones that was only trained on broadcast material. The results here are only shown for Conv-TasNet, however, the same was observed for Spleeter and Open-Unmix. If we then take a look to the comparison to the other networks, to the ones that were specifically developed for dialog separation, and maybe have a first look towards IDC, so the instant dialog cleaner, we see that all three transfer learning methods can outperform this system. Especially the negative value in improvement of signal to distortion ratio indicates that IDC introduces significant artifacts while processing the data. However, it needs to be mentioned that IDC needs to work in real time and therefore has different processing constraints. Comparing now the fine-tuned versions to DNNs, we see that DNNs outperforms the Open-Unmix model and is more or less on par with Spleeter, but gets also outperformed by the fine-tuned Conv-TasNet version. And if you take a look at the IRM, we see that it has by far the best 2F model score. If we then take a look at the perceptual evaluation, so for the listening test, here in the x-axis there are the single items, but we want to focus really on the right, where we have the average overall items. First of all, we can see that the perceptual evaluation confirms the results that fine-tuning the models works well for music source separation towards dialog separation. Overall, the DNNs then shows best perceptual performance closely followed by Conv-TasNet. And Spleeter is again the second best music separation network. However, it initially started with a worse baseline than it was previously. The results for IDC and for Open-Unmix are more or less confirmed, like in the computational metric results. If we then conclude, we can say that transfer learning from music towards dialog separation is possible, and even fine-tuning the music separation networks show competitive performance compared to solutions that were specifically developed for these tasks. And as an overall remark, like all methods benefit to varying degrees from fine-tuning with this broadcast-specific material. With this, I want to thank you for your attention, and I'm open to take questions.
Thank you for the presentation. We have now some time for the audience to ask questions. You may take the microphone in the front.
Okay, you can talk.
Hello?
Yes.
Does it work? Thanks a lot, Martin, for an interesting presentation. So I got one question related to the test results.
Yes.
It's one of the last slides that you had.
Mm-hmm.
If you could come. Okay. Yeah, so this is the results of the Mashra test, I guess,
Yes.
right? So the hidden reference, what is it? Is it the original signal, meaning that it is the broadcast audio containing both the dialogues and the original background music? No modifications into it, right?
No, the hidden reference was, as mentioned in the, if you go back here, there was the one, like the reference condition created by attenuating the background by 12 dB.
Okay. So that explains.
That's why we wanted to create an application-like scenario where the user would already attenuate the background to some extent, and yeah.
Okay, then this explains pretty much.
All right, thank you.
Well, maybe one additional question.
Please.
The same results, the LP3, LP35, it's the 3.5 kilohertz band limited reference, right?
Yes, like the low anchor is like a 3.5 low pass width. Yes.
Okay.
Yeah.
Okay. Thank you.
You're welcome.
We have more time. Any additional questions? Okay, I have some. So from the results, it seemed that even the original models pre-trained on music separation worked reasonably well.
Yes.
So what are the types of interferences in your test data? Is it also mostly music, or are there other types of interferences?
So it is, I mean, it's to some extent it's music. It is also like very commonly like stadium, like a lot of things like you would expect in a TV show or in a movie, like environmental background, like a seaside noise or forest like noise, or special effects, like a lot of special effects, like shooting or things like that.
So did you maybe try to check specifically on these recordings that have different types of noises, whether the original models also do some kind of reasonable separation?
Well, if the musical background, for instance, includes also singing voice, of course, then this would be, since it was initially supposed to do that, this is also quite well separated and targeted, like to be in dialogue, which is not the case, but over the fine tuning, this kind of gets cleaned up. But yeah, I mean, the initial results of the music separation was actually quite good. However, as I mentioned at the beginning, we are really working here with very high perceptual quality, so it needs to be really good for the user to be used at the end.
I see, thank you. So I have some more, but I will again give a chance to the audience. Yes?
So what was the stopping criterion for the early stopping that he used?
For early stopping, it was 10. Like we had a validation set, so if the loss in the validation set did not decrease, for the patients of 10.
But on which metric? That's the question.
On the validation loss.
Okay. And the loss is SI-SDRi, or?
It depends on the single method. So for Open-Unmix, it's an L2 loss, for Spleeter L1 loss, and for Conv-TasNet the same, I think.
Yeah. And so another follow-up question on the amount of training data that the pre-trained model sees,
yeah,
or that the from scratch model see, and the fine-tuned model C is probably then different, right?
Yes.
Have you looked into this? If you can train the from scratch model as long as the pre-training plus the fine-tuning?
Well, for the pre-training, it's not always known how long it was trained. At least for like for Spleeter, for example, since it's a company-based method, they don't reveal all the secrets. For training completely with random initialization, the same criterions were used then for the fine-tuning. But yeah, I mean, there was for sure quite some different amount of pre-trained data available. Like the networks were trained with a different amount of pre-trained data, and this is something that needs to be further investigated, but we can't really access the data, unfortunately.
Thank you.
Any more questions? I will then maybe ask one more. So you did both subjective and objective evaluation. Have you seen any discrepancies between these two, or basically did the objective metrics prove to be good for this task?
So generally, I mean, what we've seen definitely at the end is that the model that performed best changed at the end. Yeah? So there is always a kind of a discrepancy between the objective and subjective models. For a basic tendency, I think the objective metrics are fine, but since the perceptual quality needs to be good, we always rely really on the subjective metrics at the end.
Sure, thank you. So we can thank the speaker again.